You may have heard the phrase boiling point elevation, and this applies to mixtures where the boiling point of a solvent is increased when there's a solute in the solution. So, for instance, salt water boils at a higher temperature than pure water. So, how does the boiling point of a solution change with composition? To answer this question, let's look at our solution of acetone and chloroform, which we know to have a negative deviation from Raoult's law. What we're going to do is we're going to look at different compositions of this solution, all the way from pure acetone to pure chloroform, and we're going to let the solution boil, measure the temperature at which it boils, and then measure the mole fraction of chloroform in the gas phase and the mole fraction of chloroform in the liquid phase. The entire experiment will be done at 1 bar of pressure, and so we are measuring normal boiling points. This is a fairly complicated graph, so let's walk through this figure piece by piece. First, let's start with pure acetone. When I have pure acetone, the mole fraction of chloroform is 0. At this point, my liquid, which is pure acetone, is going to boil at the normal boiling point of acetone, which is around 329 Kelvin. Since I have pure acetone, the mole fraction of acetone in the liquid is 1, and the mole fraction of the acetone in the vapor must also be 1 because I don't have a mixture. Let's look now at pure chloroform. When I have pure chloroform, my chloroform will boil at the normal boiling point of chloroform, which is around 335 Kelvin. You'll notice that the boiling point of chloroform is higher than the normal boiling point of pure acetone, making acetone more volatile, or having a higher vapor pressure, than chloroform. In other words, it's harder to get chloroform molecules to leave the liquid and enter the gas phase. Therefore, I have to go to a higher temperature to get a vapor pressure of 1 atmosphere. Now let's look at the mixture that boils at 332 Kelvin. In this mixture, there will be a mole fraction of chloroform in the gas phase that is about 0.1, whereas the mole fraction of chloroform in the liquid phase is nearly 0.2. This makes sense because chloroform is harder to boil or less volatile, and so less of it will end up in the gas phase, and the gas phase will be enriched with acetone. There will be more acetone in the gas phase than there is in the liquid phase. Thus, we say that the gas phase is enriched with the more volatile component. For this non-ideal mixture, there is a composition around 0.6 where the mole fraction in the gas phase is equal to the mole fraction in the liquid phase. At this composition, the interactions between acetone and chloroform are maximized, giving the highest boiling point for all the mixtures that we can make. This composition, where the vapor and the liquid have the same composition, is called the azeotrope composition. In this case, we have a high boiling azeotrope because the azeotrope composition boils at the maximum boiling point of all the mixtures. It makes sense that acetone and chloroform would have a high boiling azeotrope because the interactions between acetone and chloroform in the mixture are stronger than the interactions in the pure liquids, the interactions between acetone and chloroform molecules. Stronger interactions means that I need to increase the kinetic energy of the molecules more in order to get enough of them to have a high enough kinetic energy to leave the liquid, go into the gas phase, and produce a pressure of 1 bar. The fact that the gas phase above a mixture is enriched in the more volatile component is the concept upon which distillation is predicated. Let's see what happens when I take a mixture that has 0.3 mole fraction of chloroform and I heat it up. When I heat that mixture up, it will begin to boil at about 334 Kelvin. When it begins to boil, the liquid will have 0.3 mole fraction of chloroform. However, the gas phase is going to have approximately 0.2 mole fraction of chloroform. That means that the gas phase has 0.8 mole fraction of acetone. If I take the vapor above the mixture and cool it back down until it becomes a liquid, now I have a liquid which is enriched in acetone, therefore has less chloroform. Thus I have separated some of the acetone from the chloroform. I can do the whole thing again by taking the vapor that I have just condensed, heat it up until it begins to boil. At this point it's going to boil at a lower temperature of about 331 Kelvin, and now my gas phase is going to have a mole fraction of about 0.1, a little bit over 0.1 of chloroform, or close to 90% acetone. I can cool that vapor down and then heat that vapor up till it boils, and so forth and so on until I end up with nearly pure acetone. This is fractional distillation. This is exactly what happens in a fractional distillation apparatus. But what if my liquid has a composition of 0.6 mole fraction of chloroform? If I heat that mixture up, it will begin to boil at about 337 Kelvin, but my vapor and my liquid are going to have exactly the same mole fraction. So if I condense that vapor, I will be right back where I started from, and I cannot distill a mixture of 0.6 chloroform to reduce the amount of chloroform and increase the amount of acetone, or the other way around. Therefore, an azeotrope cannot be separated by distillation.